So let's now introduce our last speaker for the morning. It's a pleasure to introduce Chandan Biswas, who is speaking about on extremizers for Fourier restriction onto the moment curve. So, Sunny yours.
Thank you. I want to thank the organizers for the invitation, and I want to thank you all for being here. I want to talk about extremizers for the Fourier restriction onto the moment curve in RD. So for a smooth, compactly supported function from RD to R, we define the Fourier transform C to be integrate f against e power minus 2 pi I x dot c with respect to the d-dimensional Lebesgue measure. For a given function f, one would like to know how f hat the Fourier transform behave when you restrict this function onto a subset of the Euclidean space. For a subset S of RT, by this I mean specifically including of this form. You restrict f hat to the set S, take the LQ norm of f hat on S. Here there is some measure associated to S. Usually one takes the Hausdorff measure on S. But in this talk, we are going to talk about submanifold. So this should be usual some k-dimensional Lebesgue measure, where k is the dimension of the submanifold. Is bounded by CPQ. CPQ is a fixed finite constant times f LP norm of f on RD. Due to its connection to PD, number theory, geometric measure theory, and many other branches of mathematics, finding bounds of this form has been one of the most fundamental problems in analysis since Stein introduced, since the early 70s. Notice that when f is L1, we can still define this. F doesn't have to be smooth and compact supported for this to make sense. So when f is in L1, this is obviously by Fourier, this is bounded in L infinity. In fact, the L infinity norm of f hat is bounded by f L1. Thus, when we can meaningfully restrict the Fourier transform of a L1 function onto any subset of RD, including sets of Lebesgue measure 0 in RD. Whereas when f is in L2, we know f hat is in L2, and in fact, it's an isometry. But since f hat can be an arbitrary L2 function, in fact, f hat, if you take the Fourier transform twice, you get back the function f modulo this multiplication by -1. So the Fourier transform can be an arbitrary L2 function. If your set S has Lebesgue measure 0, d-dimensional Lebesgue measure 0, it doesn't make sense to talk about the restricting the Fourier transform onto that set. So we can't expect inequalities of this form when P is 2 and S has d-dimensional Lebesgue measure 0. Interpolation gives the Hausdorff inequality, which says that the f at LP prime norm over all of RD is bounded above by the LP norm of f, and P has to be between 1 and 2, and here P prime is the dual exponent of P. And these are the only estimates. There are no other estimates of this form. So for all of RD, the only way you can have Fourier restriction estimate is Q equals P prime, and P has to be between 1 and 2. When S is not RD or an open subset of RD, it's necessary that if we want to have a non-trivial estimate of this form for a set S subset for S, then S must be curved. In particular, if S, the subset, sits inside hyperplane, no non-trivial restriction estimate holds. By non-trivial, I mean obviously when P is 1, we have L1 to L infinity. So there is no other estimate other than L1 to L infinity when S sits inside hyperplane. So now let's take S to be the paraboloid of dimension D. So C zeta square, zeta is in RD. This is the paraboloid in RD plus 1. In the late 60s, Stein conjectured that the following holds. For the paraboloid, if you restrict the Fourier transform of a function in R1 plus D to the paraboloid, then the LQ norm with respect to the d-dimensional Lebesgue measure now over the paraboloid is bounded by the LP norm of f if and only if there is the scaling condition between P and Q. Also, P has to be smaller than 2 times 1 minus 1 over D plus 2. Essentially what this says is that, well, we know that we can't expect L2 restriction, but the restriction conjecture essentially says that for the paraboloid, we are not doing too bad. The worst case scenario should be we are only losing 1 over D many exponents. We are only losing, we can have 1, we cannot go up to 2, but we can go up to 2 minus 1 over d. That's what the Fourier restriction conjecture says. Currently, this is known for d equals 1. This is due to Stein and Fefferman. And this is known for d equals 1. So you take the parabola in R2. We know this estimate solved. And for d bigger than equal to 2, this is currently open, although there have been many partial progress and important progress. However, it is known that the extremizers exist for this. So by extremizer, I mean there's a function f such that if we look at the supremum over all such pair or function g, so this is the operator norm, then there is a function f which saturates the operator norm, and we call this function extremizers. It's known that extremizer exists for this inequality for all restrictions pair PQ which satisfies this. If we assume that f hat maps LP to LQ, the Fourier transform map LP to LQ. This was proved by Bourgain in 98, and Michael Christ, Fossey, 100 mark, and many others in sort of for very sort of special cases. And then in 2019, Betsy Stovall, she proved that that extremizer exists in all dimensions and for all restriction pairs of this form, if we assume the restriction conjecture. So we do not know whether the restriction conjecture is true, but if we assume that the restriction conjecture is true, then for every pair PQ, there is an extremizer. Okay. We consider similar questions for Fourier restriction to curves in RD. So for the curves, the restriction estimates are much more developed. So in this talk, we are going to consider polynomial curves in RD. So for a polynomial from R to RD, we consider the restriction estimate. You take a function which is in RD, which is a function from RD to R. You restrict the Fourier transform to the curve gamma with respect to, now we take the affine Archon measure, lambda gamma dt, where lambda gamma is given by, you take the first d derivatives, gamma prime t gamma dt, take the determinant of this matrix, and take 2 over d, the power 2 over d times t plus 1. Why this particular measure? It turns out that if you have any estimate of this form with respect to any other measure mu, then the Radon-Nikodym derivative is bounded above by this affine Archon measure. So in a sense, this is the largest measure for which one can expect LP to LQ, non-trivial LP to LQ bound like this one. So when lambda gamma is not identical to 0, when lambda gamma is 0, then obviously this is true for any P and Q. When the affine Archon measure is not identical to 0, by the way, when the lambda gamma is 0, then it can be proved that the image of the polynomial lies in a hyperplane. When lambda gamma is the affine Archon measure is not identical to 0, then it is known that the Fourier restriction operator maps LP to LQ if and only if P is less than 1 plus 2 over d square plus d, and again P and Q satisfies this scaling condition. Now, one thing to notice is that, see, when d goes to infinity, we are getting close to the worst case. So even though for the paraboloid, we are only losing, let's say, 1 over d many exponents, right? We can do as much as 2 minus 1 over d. For the curved case, the best we could do is 1 plus 2 over d square plus d, which is sort of like saying essentially the reason is that for the paraboloid we have only one complementary direction. So the Fourier restriction, or rather the dual extension operator, can blow up in only one direction, whereas for curved, let's say t squared t cube in R3, the extension operator, the dual extension operator, can blow up in two complementary directions. So that's why as d goes to infinity, we're getting to the worst case. Okay, so this was proved by Betsy Stovall in 2016 in all dimensions, where she in fact proved that this constant CPQ can be taken to be independent of gamma. This depends only on d and the degree of the polynomial n. This does not in particular depend on the curve itself. And then also before that, by Bag, Oberlin, Seeger, Engineers Wright, and Drury and Solin in sort of special cases and part of the region. The question of weak bound, whether when p equals 1 plus 2 over d square plus d, whether weak type bound holds, is largely open. Okay, so our question is, the question that we are interested in does extremizer exist for Fourier restriction to curves in RD? So let's BP let's BP denote the operator norm. So if you look at the supreme over all such pairs G, which has LP norm 1 in RD, look at the Fourier transform, they the Fourier transform for the polynomial, and take the LQ norm of this function with respect to the affine activism. We say LP normalized sequence. The LP normal meaning that each Fn has LP norm 1. This is an extremizing sequence. If as limit n goes to infinity, you look at the LQ norm of the Fourier restriction of Fn to the curve, it becomes big. Finally, we know that this is already constant. So there would be, by definition, there are extremizing sequences. So this is the theorem that I want to discuss today. This is joint work with Betsy Stovall. For each pair PQ satisfying this, which was the condition that we have for Fourier extension curves, there are extremizers for the corresponding LP to LQ estimates. When gamma is the moment curve, T square T per D for in all dimensions D. Additionally, given any extremizing sequence of this this sequence which satisfies this, there's a subsequence of that extremizing sequence which converges in LP, in the Lebesgue space, and therefore that particular limit will be an extremizer up to a symmetry. Okay, so I mentioned symmetry. What do I mean by symmetry? Note that, okay, one more thing. See here, I didn't write LQ of lambda gamma because for the moment curve T square, the affine natural measure is identically the one-dimensional Lebesgue measure GT. So for convenience, we work with the dual extension operator. So the dual of the restriction operator for the moment curve is extension of f at x. For x in RD, you integrate f against e power I x dot T square T per D. So the theorem of Betsy and others would be extension map LP to LQ if and only if Q and P satisfy the scaling condition and Q is bigger than D square plus D plus 1. D square plus D plus, sorry, this should be 2, not 1. D plus 2 divided by 2. There are many symmetries of the operator. By symmetry, I mean if you change the function, there are automorphism phi of LP, so that if you change the function by phi, there is another automorphism psi in LQ, such that you change the extension applied to f by psi. So there are dilations. So if you change the function f by lambda inverse, and then also have to multiply it by lambda power minus 1 or p, so that this has the same LP norm as f. Then what happens to the extension operator is that this becomes, we take the extension operator, applied to this non-isotropic scaling, multiplied by this factor. Remember, d times d plus 1 over 2q is 1 over p prime. There is modulation if we change f by, if you modulate f by x naught, then on the physical side, the extension operator gets translated to x naught. Here x naught is a point in RD. And there is also translation. If I translate the function f to a point t naught, on the physical side, it becomes e power I x dot gamma t naught, and then extension of f applied to linear transformation at x. Here, a t0 is d by d invertible matrix, lower triangular matrix with ones on the diagonal. In particular, this is determinant 1. So this does not change the LQ norm of extension of f. So here, A is this matrix. You have 1, 1, 1 on the diagonal, and on the everything up above the diagonal is 0. Okay. Now I want to briefly discuss the proof for p equals to. Okay. Okay. How much time do you have? 16. I have around 40 minutes. 14.
I think you finish in at 12:50, right?
Yes. So how much time do I have right now?
I think you finish in 13 minutes.
Okay, thank you very much. So let's look at proof for p equals 2. So let Fn be an L2 normalized sequence. So each Fn has L2 norm 1, and limit n extension Fn LQ2 is V2. Here Q2 is the corresponding Q component. It turns out to be this is d times d plus 1 in RD. Now, because Fn is bounded, passing to a subsequence, Fn will converge to a weak limit f. So by definition, thus we have L2 decoupling in the sense that as limit n goes to infinity, Fn, the square of the L2 norm of Fn is the same as the limit of square of the L2 norm of f plus square of the L2 norm of Fn minus F. Okay, so we already have this. Now, additionally, let's suppose that we also have the same thing on the physical side. So we also have the LQ2 decoupling for the extension operator. So let's suppose that limit as n goes to infinity, you take the Q2th power of extension Fn minus extension of F, the Q2th power of Q2 norm power of Q2th norm of extension of F, and minus the extension operator apply to Fn minus F. Then take the Q2th norm power of the Q2th norm. Then this also goes to 0. We don't know whether 1.3 holds or not, but let's suppose for now that that holds. Then because this is an extremizer sequence, so B2 per Q2 is extension of Fn per Q2 per Q. Now, because we have LQ decoupling, this is bounded by the sum of these two things. Now, because extension operator is bounded, this is bounded by B2 per Q2 times the L2 norm of F per Q2 plus Fn minus F L2 norm per Q2. Remember, Q2 is bigger than 2, so what I can do, I can break each of these as this L2 square plus Fn minus L2 square times maximum of F of L2 or Q2 minus 2 and Fn minus F L2 Q2 per 2. Now remember, we have, because of L2 decoupling, this is bounded by 1. And so this is bounded by B2 per Q2 times maximum of these two quantities. Well, now if F was non-zero, let's say L2 of F is non-zero, then this is strictly less than B2 per Q. Remember, on the left-hand side, this is B2 per Q2 is a lower bound. This is strictly less than, unless if L2 is identically 1. So if we assume that the weak limit is non-zero, in the sense that the L2 norm of F is weak limit is not 0, then this is possible only when L2 norm of F is 1. So in particular, we started with this information that Fn converges to F weakly. Now we also have that the weak limit has norm 1. So the Betsy lemma gives that Fn minus F, in fact, converges Fn converges to F in L2, not just weakly, but also in norm. And therefore, F, the weak limit, being a strong limit now, will be an extremizer for the extension operator. Okay. There's a couple of things that I assumed. Okay. So the question is, how do we make sure that the weak limit F is not identically 0? Right? Given an extremizer sequence, just because it's bounded, passing to a subsequent, it will converge to a weak limit. You want to make sure that the weak limit is not identically 0. The L2 norm of F is not 0. And the second thing is, how do you establish that LQ2 decoupling for the extension operator? Both of them come out as results of an improved LP estimate for the extension operator. And this is the precise statement. So again, we start with these exponents Q and P satisfying this relation. Then there's a theta, which will depend on P, and the fixed positive constant, which will also depend only on P, such that we can bound the LQ norm of extension of F by, you take the supremum over all dyadic intervals. Supremum over all dyadic intervals, and then supremum over all non-negative integers, then 2 power minus Cpn times Fni LP norm, power 1 minus theta times F of LP theta, and this is valid for all F. Here Fni is you restrict F to the dyadic interval I. Not just that, we also bound the height of F. So Fni is also at most 2 power n times length of I power minus 1 over P. So now, if you look at this estimate, let's assume that F is F is close to being an extremizer. So extension of F LQ is very close to being the BP, which is the operator norm. Then n cannot be too large. In other words, for a near extremizer, if we look at these dyadic intervals that this theorem gives, then the height of this function restricted to this dyadic interval is approximately at most length of I power minus 1 over P. It can be too large. Okay. Okay. So this is the improved estimate. So now we'll use this to get the LQ2 decoupling for the extension operator. Again, we start with this exponents PQ satisfying the relation. For every epsilon, there is a delta such that if any f which is close to being an extremizer, in the sense that if the LQ norm of extension of f is at least the operator norm times 1 minus delta, we can just pretend that f has LP norm 1. So if f is close to being an extremizer, then there is a symmetry S. So we have to either translate or scale it, so that after applying the symmetry, if the LP norm of f outside on this set where t is bigger than r and where f is bigger than r is less than epsilon. In other words, given any epsilon, if we are allowing to lose an epsilon amount of LP mass, then every single near extremizer is supported on the fixed compact interval minus r to r. Also, it is uniformly bounded. It is at most r. So thus, modulo loss of epsilon amount of L2 mass, we can pretend that an extraneous sequence satisfies this. Each Fn is at most r and supported on minus r to r for each n. And how do I get this? Well, the improved LP decoupling, the LP estimate that we had, says that well, we can decompose the function basically into finite many dyadic pieces. So for each function, let's say we have to deal with only, let's say, first 1,000 dyadic pieces, and everything else has LP norm less than epsilon. So we start with the 1,000 dyadic pieces, and applying symmetry, we can assume that one of these dyadic pieces has length 1. So it's like 0 to 1, and the function is at most 1 on the interval. So one dyadic piece of this near extremizer is like characteristic function of the interval 0, 1. Then what this theorem says says that all these other 999 dyadic pieces cannot go to 0, cannot have arbitrary small interval, small length, which can be proved by using just Holder singularity. And the other one is that the dyadic interval cannot shoot up to infinity. And this can be proved by multilinear restriction estimate of Michael Fish. Okay, so now that we have this theorem that each Fn is uniformly supported on a fixed compact interval and uniformly bounded, now we can apply the Bridges-Leib lemma, because the extension operator, because Fn converges to F weakly, therefore the extension of Fn converges to extension of F at every point x in Rd. And now we apply the Bridges-Leib lemma to get that we have LQ2 decoupling for the extension operator, if we allow ourselves to lose an epsilon amount of LP mass. So that gives the LQ decoupling. Now, so the next question is, how do we make sure that the weak limit is not 0, identically 0? So this is given by another lemma, which basically comes from the improved LP estimate. So there is a positive finite constant C, such that given any sequence Fn which satisfies this property, that all of them are supported on minus r to r and uniformly bounded. Each Fn L2 has bound, so this sequence is bounded in L2. For us, capital A would be 1 because we are working with an L2 normalized within sequence. And the most important part of the assumption is that extension of Fn, the LQ2 normal extension of Fn is at least epsilon for each n. So each of them is large. Then there is a sequence xn, so that if we modulate Fn by xn, this will converge to a non-zero weak limit phi, not just non-zero. The LQ norm of phi would be at least epsilon power 10. So if LQ2 norm of extension of Fm is at least epsilon for each n, then the weak limit is not just 0, it's at least epsilon power 100. So now for an exponential sequence, note that we can take epsilon to be the operator norm divided by 2 for large enough n, which says that the L2 norm of f is at least a small positive constant, and thus in other words, we have non-zero weak limit, and so we have the proof for L2 decoupling. We have the proof for existence of extremizer when P is 2. Okay. Now for general P, so we look at a P between 1 and d square plus d plus 2, d square plus d plus, sorry, I can seem to see this, d square plus d plus 2 divided by 2. Unfortunately, the LP decoupling fails to hold for P equals 2, which is basically got for free for P equals. Just from definition, we had L2 decoupling because Fn converges to F weakly. So to combat this, we adapt an argument of Lyon's. This is known as the profile decomposition for L2. Again, we start with the function, sequence of function Fn, each of these supported on the compact interval minus r to r. and each of these is uniformly bounded by R pointwise. Then passing to a subsequence, there is a sequence. There are sequences X and J in RD. At every step J, there is a sequence X and J, and a non-zero function phi J, such that the following hold. You look at the phi J, we modulate this by X and J, and then you subtract this finite sum of the profiles from Fn, and we call this the error term or the remainder term at the capital J step. Okay, what are these phi J's? These phi J's are weak limit of Fn's. So for each J, phi J is a weak limit of e power I x n j dot gamma Fn. We have LQ decoupling at every step. This can be seen easily because, again, all these functions have complex support and if I'm bound, therefore the Betsy lemma will give you the LQ decoupling at every step, capital J. Negligible error. So when J goes to infinity, we look at the error term at the jth step, Rnj, take the LQth norm of the extension operator applied to Rnj, then as J goes to infinity, this goes to 0. In other words, if we allow ourselves to take countably infinite many of these profiles, phi1, phi2, and so on, then we can pretend that there is no error at all. We can write Fn simply as summation J from 1 to infinity e power minus I x n j dot gamma phi J for our purpose. And perhaps the most important part is the substitute for L2 decoupling. Which is this? We look at the LP norm of the phi J, take the p tilde power, take the sum from J from 1 to infinity. This is at most lim inf of the p tilde norm of L excuse me, p tilde power of LP norm of each Fn, where p tilde is maximum of pp prime less than q. When p was 2, p tilde is 2, so this is summation phi j L2 norm square is bounded by lim of the L2 norm square of Fn, which we got by default. I want to mention that this is important, that this inequality right here, the constant in this inequality is 1. This is very important. And also that p tilde is strictly less than q. Now the strict convexity, now that, so this, we can think of this as, we can think of this as almost LP decoupling. The strict convexity of LQ spaces, just as in the case of P equals 2 and Q equals Q2, implies that there is only one significant profile. Although, remember, we have countably infinite many profiles, it turns out that there is really just one profile and every other profile is just part of the error, which is negligible. And this can be proven this way. So the qth power of the operator norm minus little o of r, here little o of r goes to 0 as r goes to infinity, is at least is bounded above by extension operator applied to Fn. You restrict Fn to this fixed complex weight minus r to r, also where Fn is less equal to r. Now we can apply the profile decomposition to these functions to get that extension of this sequence is bounded above by, because of the LQ decoupling, this is bounded above by the qth power norm of LQ of extension of qth. I'll break this into two parts. I will write this as extension of Pj LQ norm power p tilde minus q minus p tilde. Well, now because of this almost decoupling for LP, we know that this term inside this parenthesis is at most 1, because we started with an LP normalized extremizer sequence. So this is at most 1, and we know that each Fn converges to each of these phi j is a weak limit of Fn. Therefore, each of these are at most 1. So this is less equal to Bp power q times maximum of j. I should say supremum here. Supremum of j, the LP power q minus p tilde of LP norm of phi j. So this implies that there is one profile phi j naught whose LP norm is at least 1 minus little o of r. Again, phi j naught is a weak limit of Fn modulo modulation. Weak convergence, now a large weak limit implies convergence in Lebesgue space, in fact, and that will be an extension operator. Okay, I think I'll stop it.